Mm. Hello, everyone. Today I will be presenting the paper called Data Efficient Active Learning for Structured Prediction with Partial Annotation and Self-Training. And this paper was presented in EMNLP conference in 2023. I will be following this index for the presentation. For introduction, first I will define active learning. Sorry about the noise. For active learning is the process of the model selecting the most informative data instances to reduce the annotation costs by requiring fewer labels. And active learning is a good way for structure prediction tasks. And structure prediction is a core problem in NLP where the output consists of complex structure labels made up of interdependent variables. Here, what we mean is that the output of the problem is also like for example, for named entity recognition task, the output is a the output is a label sequence that each element has interdependency. So these type of tasks are called structure prediction. As I said, named entity recognition, dependency parsing, event extraction, and relation extraction are examples of this type of problem. And applying active learning to this can be done, but in previous studies, they usually adopt full annotation for the output structures. However, the output, as I mentioned, if it's like a sentence or something, the input, if it's a sentence, then it can be divided into smaller substructures. And these substructures will have non-uniform difficulty and informativeness. So that's why we can say that partial annotation can be more efficient than full annotation. Here in the example, it's showing also for example, in this sentence, this is the dependency tree, and for only the red word, manual annotation is requested. But for this part, these substructures can be labeled using model predictions because they are like easy to predict, so we can trust the model's annotation as well. And in this case now, there are two main questions. And the first one is how to decide which substructures to select for annotation. How many of them are we going to select is the first question. And in this paper, they propose a performance predictor to estimate the error rate of selected instances and adjust the partial selection ratio accordingly. So this is a automatic and adaptive approach. And the second question is how to better handle the unannotated data. So we will annotate some of the stuff like this, choosing, but then some other part of the data will be left unannotated. How can we handle this? We will use self-training, and they find the unselected substructures, and these substructures are typically highly confident, and they are likely to be predicted correctly without requiring any additional annotation. So they use self-training for these type of this type of data. And the paper's framework can be summarized into one sentence, and it's a partial annotation mechanism to reduce the annotation cost that uses adaptive error estimator to select the substructures for annotation and uses self-training to pseudo-label the unannotated substructures. In this paper, what they mean by annotation cost is the reading cost plus the labeling cost. I will explain this in more detail in rest of the presentation. And they evaluate on 4 benchmark tasks, and I already listed them in the previous slide. And as a result, they show that partial annotation can obtain the same performance as full annotation with the same reading cost, but with less labeling cost, which shows us that it's a more efficient way and the annotation cost in total is reduced. And for related work, we can divide it into three: self-training, partial annotation, and active learning for structured prediction. Self-training is already proven effective in a variety of NLP tasks to incorporate unlabeled data. And it can be especially helpful in low resource scenarios, like in few-shot learning. And partial annotation is also has been explored for structured predictions, but there are other methods to deal with incomplete annotations here as well. And for active learning for structured predictions, active learning has been used in this type of task a lot, like sequence labeling, parsing, semantic role labeling, and machine translation. But most of the existing work adopt full annotation for active learning, but in this paper, they use partial annotation to reduce the annotation cost. And for the methodology, the first thing is the active learning step. They use a pool-based active learning setting, and this means that they iteratively select and annotate instances from unlabeled data pool. And there's a two-step selection approach. They first choose the batch of sentences, and then they annotate within these batches. And here for sequence labeling, they explain some of the steps, but for other type of tasks, it will be similar to this also. So they said for sentence selection, they first of all decide on the batches, and for the batch size, they use number of total tokens. Since if they chose number of sentences for batch size, it could be a problem since sentences have variant lengths. So here they first set a number of total tokens, and they take this many tokens and the sentences that they are in. And then the sentence level uncertainty is obtained by averaging the token level ones. And then the most uncertain sentences are selected. And for token selection, they use a adaptive strategy that decides how many highly uncertain tokens to select. I will explain this later again. And for annotation, they annotate the entire span that contains the query token. For example, I put here a simple example for named entity recognition task. In this sentence, if let's say the name was selected as a token in this stage, then if this name was selected, it will be annotated. But since here the named entity is the name plus the last name, in the annotation step, they annotate this entire span. Name and the last name will be labeled as a named entity, like as a person. So this is the type of annotation annotation strategy they used. And for model learning, they use different loss functions for full annotation and partial annotation. And the second part is the adaptive partial selection part to select the highly uncertain substructures within the selected sentences. So normally in other studies, how many substructures that will be selected is chosen with a predefined threshold or a selection ratio. But there are two main problems with this approach because it's hard to specify just one value. If too many substructures are selected, then partial annotation becomes like full annotation. But if not enough substructures are selected, then the model doesn't have sufficient data to train. And it needs to be adaptive because as the model trains in active learning, there are cycles, and as the model trains, the informative substructures become less dense. And as a solution, they propose a adaptive way, and it's to rank the substructures based on uncertainty score and choose the highest ones by the ratio. And here the intuition is that the incorrectly predicted substructures are the most informative ones. Like we need to annotate them manually because they are being incorrectly predicted. And here the unlabeled pool actually doesn't have annotation, so the error rate cannot be directly obtained. For this, they use a one-dimensional logistic regression model, and they train it on a development set. And the development set has the ground truth information. So the model is trained, and then we give the uncertainty scores for the trained model is taken into a prediction mode now, and the input is the uncertainty scores of the substructures in the unlabeled pool, and the output is the binary prediction, whether prediction is confidently correct or not. And this way, for each candidate substructure S, the estimator gives a correctness probability, and we get the R value, the selection ratio. And you can see here that the selection ratio can be set adaptively according to the model's capability at that moment. If the model is weak, then the larger ratio will be taken for annotation. And as the model is trained, the ratio will drop down, and this will avoid wasting annotation costs. And for self-training, for partial annotation, they select the highly uncertain substructures, as we mentioned like now, and then except those, there are the unselected substructures, and they will be pseudo-labeled. And also at each cycle of active learning, they will add the updated annotation of the selected substructures to further enhance the pseudo-labeling as well. So not only because of the self-training iterations, but also because of the increase in the annotation data here, the performance will increase. And they adapt a soft version of self-training to avoid the negative influence of ambiguous predictions. They set an uncertainty threshold and utilize only the highly confident substructures. Here, the threshold is the confidence score for self-training. So for this, we don't need ground truth labels. That's how they can do it. And this is the self-training objective function. Here, the first element here is the, sorry. Here is the results with the previously distribution of the results with the previously trained model, and this is the distribution of the results with the currently training model, and this is the self-training objective function. And for the experiment, for the tasks and data sets, as I mentioned, they use the 4 NLP tasks, the named entity recognition, dependency parsing, event extraction, and relation extraction. They use separate data sets for all tasks. And for active learning, they set the batch size as 4,000 tokens, and this is almost 2% of the total pool size. And they set the active learning cycles as 14 for each experiment. And at each cycle, they retrain the model. And in full annotation, all the substructures are annotated for the selected sentences. And in the partial annotation, they first decide the selection ratio and then apply it to the selected sentences. And for the model and training, they use a pre-trained Roberta model, but they stack the task-specific structure predictors over this model, and the full models are fine-tuned at each training iteration. And at each active learning cycle, they train the model based on all full or partial annotations. And for self-training, as I said, they use the newly trained model to assign pseudo labels to all unannotated instances and combine them with the existing annotations to train another model. And for partial annotation, since in partial annotation, there's first sentence selection, and then within those sentences, there's token selection. Here, pseudo labeling is done to both unselected sentences and to unannotated substructures in the selected sentences. And to compare the full annotation and partial annotation fairly, we need a common cost measurement. And For the labeling cost, using the number of the labeled substructures is a reasonable metric, but in the paper they say that using reading time as a considering reading time as reading cost is important as well. So they add the reading cost as well. So the reading cost is the effort required to read the context that the annotator must process. And for this to be fair comparison, they choose the same amount of context in the sentence selection step of each active learning cycle for both of the scenarios. And they say that if the partial annotation achieves similar performance to full annotation, while maintaining the same reading cost but fewer annotations, then we can say that partial annotation is more cost efficient. And in the experiments, they show this. So first, for the named entity recognition and dependency sparsity experiments, they actually compare four different strategies. First is full annotation, second is partial, and then the third is a baseline where randomly selected sentences are fully annotated. So it's like full annotation, but there's not even the sentence selection step. And there is the supervised case where the model is trained with the full original training set. And the results show that the active learning, if we compare the green lines to red and blue lines, active learning improves the random baseline and also almost reach the fully supervised performance with a small portion of data annotated. Here you can see that the number of data annotated here is quite small. And also self-training is helpful for all strategies. It improves performance for all of them. And sorry, not performance, it lowers the cost for all of them. And also with self-training, partial annotation can almost match the performance of full annotation with the same amount of reading cost while labeling fewer substructures. And for ratio analysis, as we mentioned, they use an adaptive ratio scheme. Here they do the experiments only on the dependency parsing task as a case study, and they compared adaptive results with the predefined ratio values. And here it can be seen that if the value is too small, the performance lags behind others with the same reading context due to fewer substructures annotated. But if the value is too large, it grows slowly because there's too many uninformative substructures being annotated. With these results, we see that actually R equals 0.3 is like a good decision. It's a good choice, but it's hard to find the spot each time for each task. So still they say their adaptive idea is better than these predefined values. And they also do experiments for domain transfer. They add out-of-domain annotated data to the unlabeled in-domain data and performed active learning on the target domain. The target domain is set as tweet text, and the source domains are the same for the named entity recognition and the dependency parsing tasks. And for named entity recognition, the results show that without transfer learning, here in the experiments, they are trying to see between transfer learning versus no transfer learning. So without transfer learning, the named entity recognition results are generally worse, but still similar. But we can say that transfer learning boosts the results. But for dependency parsing, we see the larger benefits of transfer learning. They do this experiment just to show that combining active learning and transfer learning can lead to good results. But yeah, they just do this for as an inspiration for future work. And the last experiment is the information extraction tasks. Here, as we mentioned, they do experiments with event extraction and relation extraction as well. Since these two tasks are related to each other, for the sentence selection stage, they use a sentence-wise uncertainty score that uses the uncertainty scores for both mention extraction and the relation between these mentions. And for the beta value, they set it as 0.9. They say this is based on previous studies. And for partial selection, they select the substructures using the same adaptive selection scheme. And if there is an error in the mentioned pair, because first we find the mentioned pairs and then we find the relation between them. So if there is an error in the first task, then system tries to match the ground truth for the relation extraction. But if both mentions in the pair are wrong, they are unrelated, but they were paired, then the entire relation pair is discarded to avoid propagation errors, and they increase the partial ratio because like this there can be some discarded pairs, so to match the values they increase the partial ratio here, and the experiment results can be seen here. For these tasks also, self-training is, by the way, here the task is put together, the two tasks, and self-training is helpful for all of the active learning strategies here as well. And partial annotation learns fastest, and labeling cost is half of full annotation. To reach the supervised results, it can be seen here. And partial annotation is also competitive in reading cost and can match the full annotation results in later active learning stages. And to conclude, the insights in the paper are they investigate a active learning strategy for structure prediction in NLP, and they introduce a performance estimator to automatically determine the optimal ratios for substructure selection, and they use partial annotation and self-training together, and these methods efficiently utilize the unlabeled data and also enhance the data efficiency. Findings show that partial annotation with self-training can demonstrate higher data efficiency compared to strong full active learning baselines, and they validate these through comprehensive experiments. There are some limitations of the paper. They say that the experiments were based on simulations with existing annotations. They say that this limits the real-world applicability of this methodology. And also, as I mentioned, there's still a dependency on a labeled development set for the error estimator. So this is a limitation. And also, they kind of simplify the information extraction experiment. They just kind of focus on the second subtask. By discarding the unrelated pairs for the first task, they say in the future both tasks can be focused, and yeah, they say dynamic balancing can be used for this. And yeah, these are the limitations, and thank you for listening.